March 2025, something unusual begins to happen in our night sky. Saturn, the planet we've always known as the Lord of the Rings, starts to look different. Its famous rings, normally bright and unmistakable, fade almost completely from view, not because they're gone, but because Earth lines up with the thin edge of Saturn's ring plane. For a short window of time, those massive structures become nearly invisible to us. It's a reminder that even the most iconic features in our solar system can change depending on where we're standing and how closely we're paying attention. But Saturn's disappearing act is just the surface of the story, because right as its rings slip out of sight, scientists uncover evidence that Earth, our own planet, once had a ring system of its own, roughly 466 million years ago. At the same time, tiny distant worlds in the outer solar system are turning out to have rings we never expected. Mars is slowly preparing to form a ring of its own when Phobos breaks apart. And in the far reaches of the Kuiper Belt, we found rings that shouldn't exist at all. Rings that violate the very physics we use to explain them. We're living in a moment where discoveries are coming faster than theories can be rewritten. Every new observation challenges something we thought we understood. Every ring system, large or small, bright or faint, adds another piece to a puzzle that stretches across the entire solar system. If you're fascinated by how these structures form, evolve, and reshape the worlds around them, you're in the right place. This is Whispering Wonders of Science, and we create long-form explorations just like this one. If you enjoy these deep dives into the hidden architecture of the universe, consider subscribing. It helps us bring you more journeys into the cosmos. Now, let's open the cosmic jewelry box and see what's really inside. To begin, we need to correct one of the biggest misconceptions people still have about ring systems. Most people picture Saturn's rings as giant solid disks, smooth like polished metal, or enormous spinning CDs. But that image has nothing to do with reality. Planetary rings aren't solid structures, not even remotely. A ring is a collection, a vast swarm, of countless independent particles. Some are tiny, no bigger than grains of sand. Others are massive, the size of boulders, cliffs, or even small moons. They're made of ice, dust, rock, and in some cases, materials we still haven't fully identified. Each particle follows its own orbit, its own trajectory, its own path, all governed by gravity, momentum, and the incredibly precise mathematics of orbital mechanics. And together, these countless moving pieces create something extraordinary. From far away, rings look smooth and solid because you're seeing trillions of particles blending into one shimmering plane. Up close, they behave more like a murmuration of starlings, those huge flocks of birds that twist and ripple across the sky. Individually, each bird moves on its own, but together, they form patterns that look almost alive. The physics behind this is just as beautiful. Every planet, moon, and massive object in space has an invisible zone around it called the Roche limit. Inside this boundary, the tidal forces from the parent body are stronger than the gravity holding a smaller object together. Cross this line, and a moon can't survive intact. Debris doesn't form new worlds. It's pulled apart, flattened, stretched, and sculpted into a ring. This is where rings live, in the cosmic danger zone, where gravity becomes a sculptor rather than a glue. But here's the part that surprised scientists in recent years. The Roche limit isn't the absolute rule we once believed it was. In 2023, a discovery in the outer solar system challenged everything we thought we understood about how rings should behave. A discovery that broke the rules in a way no one saw coming. We'll get to that soon. For now, remember this: rings are temporary. They're dynamic. They're constantly shifting, spreading, and evolving. They are not just ornaments. They are laboratories where we witness gravity, collisions, and planetary formation playing out in real time. Every ring system has a history. Some are stories of destruction, some are stories of creation, and a rare few challenge the very physics we rely on to understand the universe. Let's start with the undisputed champion, the planet that defined what it means to be ringed, Saturn. When Galileo Galilei first pointed his primitive telescope at Saturn in 1610, he saw something strange. The planet appeared to have handles or ears on either side. His telescope wasn't powerful enough to resolve the true nature of what he was seeing, so he wrote cryptically about Saturn's odd appearance. It wasn't until 1655 that Christian Huygens, using a better telescope, correctly identified these features as a ring encircling the planet. And what a ring system it turned out to be. Saturn's rings span an incredible distance. From edge to edge, they stretch nearly 282,000 kilometers. That's about 175,000 miles. Yet despite this enormous width, they are incredibly thin. If you could slice through Saturn's rings from top to bottom, most regions would measure only 10 to 30 meters thick. That's about the height of a 3 to 10-story building. To put this in perspective, if Saturn's rings were the size of a football field in width, they'd be thinner than a sheet of paper. The rings aren't uniform, though. Through telescopes, we can distinguish several main regions, each with its own character. The A ring, the B ring, the C ring, each separated by gaps like the Cassini division, a 4,800-kilometer wide dasham between the A and B rings, discovered by Giovanni Cassini in 1675. Modern spacecraft have revealed that these main divisions are just the beginning. There are thousands of ringlets, waves, and structures within structures. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered that the rings are far more dynamic than anyone imagined. Waves ripple through them, particles clump together and disperse, tiny moonlets plow through the ice, creating propeller-shaped disturbances visible from space. But here's something that shocks most people. Saturn's rings might be young, ridiculously young. For decades, scientists assumed the rings formed alongside Saturn itself, about 4.5 billion years ago when the solar system was born. But data from Cassini's grand finale, when the spacecraft dove through Saturn's atmosphere in 2017, revealed something unexpected. The rings are surprisingly pure and bright, with very little rocky material mixed in. Over billions of years, they should have been darkened by micrometeorite impacts and cosmic dust. The conclusion? Saturn's rings might be only 10 million to 100 million years old. In cosmic terms, that's practically yesterday. The rings might have formed when dinosaurs were already walking on Earth, or even more recently. This raises a profound question. If Saturn's rings are temporary, are we just incredibly lucky to be alive during the brief cosmic moment when Saturn has rings? Or do planets like Saturn cycle through periods of having and not having rings? We don't know yet, but the fact that we're even asking these questions shows how much these observations have revolutionized our understanding. And speaking of observations, let's talk about what's happening right now in 2025. Every 13 to 15 years, Earth passes through Saturn's ring plane. When this happens, the rings appear edge-on from our perspective. Remember how thin they are? When viewed edge-on, they essentially disappear from view, even through powerful telescopes. The last time this happened was in 2009. And it's happening again now, in 2025. On March 23, 2025, Saturn's rings vanished. They'll gradually reappear over the following months, disappear again in November 2025, and then slowly become visible again. By 2027, Saturn's rings will be fully visible for another 13 to 15 years. During these ring plane crossings, scientists get unique opportunities. With the rings not overwhelming Saturn with their brightness, astronomers can spot tiny moons that would otherwise be lost in the glare. In previous ring plane crossings, 13 of Saturn's 148 known moons were discovered, including Titan, its largest moon, and Mimas, one of its smallest. Saturn's rings aren't just beautiful, they're a Rosetta Stone for understanding planetary systems, a natural laboratory where we can watch orbital mechanics and particle physics play out on a grand scale, and a reminder that even the most permanent-seeming features of our solar system are temporary, fragile, and more precious because of it. Let's dig deeper into Saturn's age paradox, because it reveals something fundamental about rings everywhere in the solar system. When Cassini made its final plunge through Saturn's atmosphere on September 15, 2017, it wasn't just a spacecraft's swan song. It was a deliberate scientific sacrifice. During those final orbits, Cassini dove between Saturn's clouds and the innermost edge of its rings, a region no spacecraft had ever explored. The spacecraft was essentially skimming the top of Saturn's atmosphere while the rings screamed past overhead. During these passes, Cassini's instruments measured how much material was raining down from the rings onto Saturn's atmosphere. And the answer was shocking. A lot. Far more than scientists expected. The rings are constantly losing material. Every second, thousands of kilograms of ring particles spiral inward, pulled by Saturn's gravity and atmospheric drag. At this rate, the rings can't last more than a few 100 million years into the future. Combined with their surprising brightness and purity, this led scientists to a radical conclusion: Saturn's rings are young. But this creates a paradox. If rings are so temporary, so fragile, so quick to disappear on cosmic timescales, why does Saturn have them right now? What are the odds that we'd exist during the precise moment in Saturn's 4.5 billion year history when it happens to have spectacular rings? Some scientists argue we're just lucky. The universe is vast and unlikely things happen all the time. Maybe we're living during Saturn's brief ringed phase, and for most of its history, Saturn looked as naked as Jupiter. Others suggest something more intriguing. Maybe Saturn cycles through rings. Perhaps every few 100 million years, a moon wanders too close, gets torn apart, and creates a new ring system. The current rings die, but new ones are born from cosmic collisions and orbital decay. Under this model, Saturn might have rings most of the time, just not the same rings. Recent research published in 2024 suggests that rings might even play a role in forming moons, which then migrate outward, decay, and eventually form new rings. It's a cosmic recycling program where moons and rings are two phases of the same material, transforming back and forth over millions of years. This paradox extends beyond Saturn. We're discovering that rings might be far more common and more temporary than we ever imagined. They're not permanent fixtures, but transient phenomena, like rainbows or auroras, there for a moment in geological time, then gone. And if rings are temporary everywhere, if they come and go on timescales of millions rather than billions of years, then the universe might be full of planets and moons going through ringed phases. We might be living in a cosmos where rings are constantly appearing and disappearing, where the cosmic jewelry box is always being rearranged. This isn't just philosophy. It's testable science. And as we're about to see with the other planets, the evidence is mounting that rings are indeed everywhere, far more common and varied than we ever dared imagine. While Saturn steals the spotlight, Jupiter quietly harbors its own ring system. And quietly is the operative word, because Jupiter's rings are so faint, so dusty, and so elusive that we almost missed them entirely. The story of Jupiter's rings begins with Voyager 1 in 1979. As the spacecraft approached Jupiter, mission planners decided to take a chance. They knew Saturn had rings. Uranus had recently been discovered to have rings in 1977. So why not look for rings around Jupiter? It seemed like a long shot. If Jupiter had rings, surely we would have spotted them by now through telescopes. But Voyager 1 was equipped with cameras far more sensitive than anything ground-based telescopes could achieve, and it would be taking pictures from a vantage point impossible from Earth. On March 4, 1979, Voyager 1 took a long-exposure image looking back at Jupiter with the sun behind the planet. And there it was, a faint ring glowing dimly in backscattered sunlight. Jupiter had rings, We just couldn't see them from Earth because they're made of material that doesn't reflect light well. The particles are tiny, mostly microscopic dust grains. They're not icy and bright like Saturn's rings. They're dark, small, and scattered, more like a tenuous halo than a solid disk. The Galileo orbiter, which studied Jupiter from 1995 to 2003, revealed that Jupiter's ring system consists of 4 main components. First, there's the main ring, extending from about 122,500 to 129,000 kilometers from Jupiter's center. This is the ring Voyager spotted, made of dust particles ejected from 2 small moons, Adrastea and Metis, which orbit within the ring. Second, there's a thick inner torus, called the halo ring, extending inward from the main ring toward Jupiter. This halo is created when electromagnetic forces push particles out of the main ring plane, creating a diffuse cloud. Third and fourth, there are 2 faint gossamer rings, much farther out, associated with the moons Amalthea and Thebe. These rings are incredibly tenuous, more like dust clouds than structured rings. What's fascinating about Jupiter's rings is that they're constantly being replenished. Unlike Saturn's rings, which might have formed from a single catastrophic event, Jupiter's rings are fed by ongoing dust production. Micrometeoroids constantly bombard Jupiter's small inner moons, blasting dust particles into orbit. Without this continuous supply, Jupiter's rings would fade away in mere decades or centuries. This makes Jupiter's rings fundamentally different from Saturn's. Saturn's rings are ancient, or at least millions of years old, made of larger particles held together by gravity and electromagnetic forces. Jupiter's rings are ephemeral, a dust cloud constantly regenerating from the destruction of its source moons. Io, Jupiter's volcanic moon, plays a role too. Io's volcanoes spew material into space, some of which gets ionized and swept up in Jupiter's powerful magnetic field. This creates an invisible torus of charged particles around Jupiter, which interacts with the ring system in complex ways. Jupiter's rings remind us that not all ring systems are created equal. Some are bold and dramatic, others are subtle whispers, barely visible even to spacecraft flying through them, but each tells a story about the environment around its planet, the history of its moons, and the ongoing processes that shape planetary systems. Uranus is weird. Let's just get that out of the way. While most planets in the solar system spin like tops, with their axes roughly perpendicular to their orbital planes, Uranus is tilted 98 degrees. It essentially rolls around the sun on its side. This bizarre orientation likely resulted from a massive collision early in the solar system's history, an impact so violent it knocked Uranus onto its side. And Uranus's rings? They are just as strange as the planet itself. The discovery of Uranus's rings was accidental and brilliant. On March 10, 1977, astronomers were preparing to watch Uranus pass in front of a distant star, an event called a stellar occultation. By watching how the star's light dimmed as Uranus crossed in front of it, scientists hoped to learn about Uranus's atmosphere. But something unexpected happened. Before Uranus reached the star's light blinked multiple times in a pattern. Then Uranus passed in front, blocking the star as expected. And after Uranus moved away, the star blinked again in the same pattern but reversed. The conclusion was inescapable. Uranus had rings. It wasn't just one ring. The blinking pattern revealed at least 5 distinct rings, and subsequent observations found more. Today, we know Uranus has 13 distinct rings, named in order of discovery. The innermost rings are designated Zeta, 6, 5, 4, Alpha, Beta, Eta, Gamma, Delta, Lambda, Epsilon, Nu, and Mu. Uranus's rings are narrow and dark, made of material that reflects very little light. They're not icy and bright like Saturn's rings, but rather composed of dark particles, possibly radiation-processed organic compounds and water ice. The particles range from tiny dust grains to boulders several meters across. The Epsilon ring, the outermost and most prominent, is particularly fascinating. It's incredibly narrow, only about 20 to 96 kilometers wide, but it maintains this narrow structure across its entire circumference. How? Shepherd moons, small satellites orbiting just inside and outside the ring, gravitationally confine the particles, preventing them from spreading out. For decades, our view of Uranus's rings remained limited to those initial observations and brief glimpses from Voyager 2, when it flew past in 1986. The rings were known to exist, but their details remained fuzzy. Then came the James Webb Space Telescope. In 2023, Webb turned its infrared eyes toward Uranus and captured the most detailed images of the planet's rings ever obtained. The images are stunning. They show not just the main rings, but also the fainter dusty rings that were barely visible before. Webb's sensitivity revealed the ring's structure in unprecedented detail, showing variations in brightness and width that hint at complex gravitational interactions. What's particularly exciting is that Webb can study Uranus's rings in infrared light, revealing their composition and temperature in ways visible light cannot. This is crucial because Uranus is so far from the Sun, over 2.8 billion kilometers, or 1.7 billion miles, that sunlight barely reaches it. The planet and its rings are incredibly cold, around minus 224 degrees Celsius, or minus 371 degrees Fahrenheit. At these temperatures, many substances behave differently, and Webb's infrared vision lets us see how. Uranus's sideways orientation creates unique seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness as Uranus orbits the Sun. The rings, tilted along with the planet, experience these extreme seasonal changes too. How do the rings respond? Do they change composition or structure as the Sun moves from pole to pole? These are questions Webb's observations are beginning to answer. Uranus's rings prove that ring systems don't need to be spectacular to be scientifically valuable. They're a laboratory for studying narrow rings, shepherding dynamics, and how ring systems evolve in the cold outer reaches of the solar system. If Uranus's rings are mysterious, Neptune's rings are downright enigmatic. Neptune, the solar system's most distant major planet, is a blue world of supersonic winds and dark storms. Voyager 2 discovered its rings during its flyby in 1989, but even before that, astronomers suspected something was there. Stellar occultations in the 1980s showed odd patterns. Sometimes Neptune seemed to have rings. Other times, it didn't. The data was maddeningly inconsistent. Some observations showed clear dips in starlight suggesting rings, while others showed nothing. The solution to this mystery? Neptune's rings are incomplete. Unlike every other ring system in the solar system, Neptune's rings aren't continuous. They have dense clumps or arcs where most of the material concentrates, separated by nearly empty gaps. It's as if someone tried to build a ring around Neptune, but only got partway done. Neptune has 5 main rings: Gale, Leverrier, Lassell, Arago, and Adams. The Adams ring is the most interesting because it contains the prominent arcs. These arcs have been given names: Fraternité, Égalité, Liberté, and Courage. Each arc is a dense clump of ring particles confined to a small section of the ring. The big question: why don't these arcs spread out? Orbital mechanics suggests that particles in a ring should eventually distribute themselves evenly. Material from dense regions should gradually move into sparse regions until the entire ring has uniform density. Yet Neptune's arcs have persisted for decades, defying this expectation. The answer, as with Uranus, involves shepherd moons. The moon Galatea orbits just inside the Adams ring, and its gravity interacts with the ring particles through orbital resonances. These resonances trap particles in specific locations, preventing them from spreading out. It's like gravitational shepherding, taken to an extreme, not just narrowing the ring, but creating discrete clumps within it. But here's the troubling part. Neptune's rings are dying. Observations from the Hubble Space Telescope and ground-based telescopes over the past few decades show that the arcs are fading. They're not as bright as they were when Voyager 2 first imaged them in 1989. The rings are losing material faster than they're being replenished. Why? We're not entirely sure. It could be that the shepherd moon Galatea isn't as effective at confining particles as we thought. Maybe the source of ring material, likely impacts on small moons, has slowed down. Or perhaps Neptune's rings were never meant to be permanent, and we're witnessing their final act. This raises a profound possibility. Maybe we're lucky to see Neptune's rings at all. If they're actively fading, there must have been a time when they were much brighter, and there will be a time in the future when they disappear entirely. We might be living during the brief window when Neptune happens to have visible rings. Neptune's rings are a reminder that ring systems are dynamic, evolving, and temporary. They're not static decorations, but active participants in the ongoing story of planetary systems, constantly created, sustained, and eventually destroyed by the complex dance of gravity, collisions, and orbital mechanics. We've mentioned the Roche limit several times, but now it's time to truly understand why this invisible boundary is so crucial to the existence of rings. Imagine you're standing on a small moon orbiting close to a massive planet. The planet's gravity pulls on you, but it doesn't pull evenly. The side of the moon facing the planet feels stronger gravity than the side facing away. This difference in gravitational force is called a tidal force, the same phenomenon that creates ocean tides on Earth. Now imagine moving closer to the planet. The tidal force increases. The difference between the gravity pulling on the near side versus the far side becomes more extreme. At some point, this tidal force becomes stronger than the moon's own gravity holding it together. That point is the Roche limit. The exact distance depends on the density and structure of the moon and the mass of the planet. But for a moon made of solid rock or ice, the Roche limit is typically about 2 to 3 times the planet's radius. Inside this limit, moons cannot exist. They get torn apart, shredded into debris that spreads out into a ring. This is why all ring systems orbit close to their parent bodies. It's not a coincidence. Rings exist inside the Roche limit because that's where the physics forces them to exist. Or so we thought. The Roche limit isn't just a theoretical curiosity. It's actively shaping our solar system right now. Saturn's moon Enceladus orbits right at the edge of Saturn's Roche limit, and tidal forces constantly flex and squeeze its interior, generating enough heat to maintain a subsurface ocean and power the geysers that spray water into space. Mars's moon Phobos is slowly spiraling inward about 2 meters per century toward Mars's Roche limit. When it crosses that boundary in 30 to 50 million years, Phobos will be torn apart, creating a ring system around Mars. The Roche limit also explains why ring particles don't clump together to form new moons. Inside the Roche limit, gravity pulls particles apart faster than they can stick together. Outside the Roche limit, particles can accumulate and grow. This is why shepherd moons orbit just outside the main rings. They formed from particles that escaped the Roche limit and coalesced. But as we've hinted, the Roche limit isn't the absolute law we once thought. Recent discoveries have found rings existing well beyond where they should be able to survive. These findings are forcing us to reconsider everything we thought we knew about ring formation and stability. The Roche limit is still important, still relevant, but it's not the whole story. And that's what makes the next chapter of ring discovery so exciting. Until 2013, rings were exclusive to big planets. Jupiter, Saturn, Uranus, Neptune, these giants dominated the ring game. The idea that a small asteroid could host rings seemed absurd. Asteroids don't have enough mass, enough gravity, to hold rings in place, right? Wrong. On June 3, 2013, a team of astronomers was observing a stellar occultation by Chariklo, a small body orbiting in the outer solar system between Saturn and Uranus. Chariklo is classified as a centaur, a class of icy asteroids that orbit in the region of the giant planets. It's only about 250 kilometers, or 155 miles in diameter, tiny by planetary standards. As Chariklo passed in front of a distant star, astronomers watched the star's light dim as expected. But then, something unexpected happened. Before and after the main occultation, there were two additional dips in brightness, perfectly symmetrical. Short but distinct. The interpretation was stunning. Chariklo has rings. Not just one ring, but two distinct, narrow rings orbiting this tiny asteroid. The rings were nicknamed Oiapoque and Chuí, after two rivers that mark the northern and southern borders of Brazil, in honor of the Brazilian astronomers who led the discovery. This was revolutionary. It was the first time rings had been discovered around a body smaller than a planet. It shattered the assumption that rings required massive planets to exist. Chariklo's rings are remarkably narrow, just a few kilometers wide, and they orbit incredibly close to Chariklo's surface. The inner ring, Oiapoque, is about 6 to 7 kilometers wide and orbits at a distance of about 391 kilometers from Chariklo's center. The outer ring, Chuí, is even narrower, about 3 kilometers wide, orbiting at about 405 kilometers from the center. How do such narrow rings stay confined? The answer again involves shepherd moons. Astronomers believe Chariklo must have at least one small moon, too small to detect directly, that gravitationally sculpts the rings and prevents them from spreading out. Or possibly, Chariklo's elongated shape and relatively fast rotation create orbital resonances that confine the rings. The discovery raised immediate questions. If Chariklo has rings, do other centaurs have rings too? What about other asteroids? In 2015, another centaur named Chiron showed evidence of possible rings during stellar occultations, though the data is less conclusive than for Chariklo. If confirmed, it would suggest that rings among small bodies might be more common than we ever imagined. In 2024, researchers published simulations showing that Chariklo's rings can be maintained by a tiny shepherd moon, and they used models developed for studying Saturn's rings to understand how ring particles around such a small body behave. Chariklo's rings are likely made of water ice, similar to Saturn's rings, but much darker. They might have formed from a collision that shattered a small moon, or from debris ejected during an impact on Chariklo itself. The exact origin remains uncertain, but their existence alone is profound. Chariklo proved that rings aren't exclusive to giant planets. They can exist around small bodies too, as long as the conditions are right. This opened the door to a new era of ring discovery, one that would soon extend even farther into the outer solar system. Haumea is one of the strangest objects in our solar system, and that's saying something in a solar system that includes worlds with subsurface oceans, planets that rain diamonds, and moons with liquid methane lakes. Haumea is a dwarf planet orbiting in the Kuiper Belt, the region of icy bodies beyond Neptune. It's roughly the same width as Pluto but shaped nothing like it. Haumea is shaped like a stretched out football or a flattened egg, with dimensions of roughly 1,900 by 1,600 by 1,000 kilometers. Why such a bizarre shape? Haumea spins. Fast, incredibly fast. A day on Haumea lasts just under 4 hours, making it the fastest rotating large object in the solar system. This rapid rotation has flung material outward, stretching Haumea into its elongated shape. Haumea has two known moons, Hi'iaka and Namaka, both likely fragments from the same collision that set Haumea spinning. And as astronomers discovered in January 2017, Haumea has something else, a ring. The discovery came during a stellar occultation. A network of 12 telescopes spread across 10 locations in Europe watched as Haumea passed in front of a star. The observations revealed not just Haumea's size and shape, but also brief dips in starlight, consistent with a ring of material orbiting the dwarf planet. This was huge. Haumea became the first object beyond Neptune confirmed to have a ring, and only the third small body overall, after Chariklo and possibly Chiron. The discovery suggested that rings might be common in the distant reaches of the solar system, not rare anomalies. Haumea's ring is about 70 kilometers wide and orbits roughly 1,000 kilometers from Haumea's surface, lying in the plane of Haumea's equator. It's likely made of ice ejected during collisions, or perhaps material left over from the event that created Haumea's moons. What makes Haumea's ring particularly interesting is that it challenges theories of ring stability. For a ring to survive around such a small body with such a strange shape requires specific conditions. The ring's location coincides with a 3-to-1 orbital resonance with Haumea's rotation. This resonance might play a key role in keeping the ring stable, preventing particles from either falling onto Haumea or escaping into space. One theory suggests that Haumea's odd shape, fast rotation, moons, and ring are all connected. About 1 billion years ago, Haumea might have collided with another large Kuiper Belt object. The impact shattered both bodies, sending fragments flying. Some fragments became Haumea's moons. Others formed a debris disk that eventually settled into the ring we see today. The collision also set Haumea spinning at its current breakneck pace. This would make Haumea's ring relatively young, just a few 100 million years old, similar to the proposed age of Saturn's rings. It would mean we're observing Haumea during a brief window in its history when it happens to have a ring. Haumea's discovery proved that rings can exist around dwarf planets in the Kuiper Belt, setting the stage for what would become one of the most significant ring discoveries in recent history. And that brings us to another frontier entirely, farther out, deeper into the Kuiper Belt, where things get even stranger. Here lies one of the true troublemakers of the solar system, a dwarf planet that refuses to follow the rules. A world that has astronomers scratching their heads because on paper what it's doing simply shouldn't be possible. Meet Quaoar. Quaoar is not a household name like Pluto or Eris. It doesn't have a flashy atmosphere, it doesn't have geysers, and it doesn't have a dramatic tilt. But what it does have is something far more interesting, a ring system that should not exist. Here's the problem. According to every model, every textbook, and every calculation going back decades, rings can't survive outside a region called the Roche limit. The Roche limit is simple. Get too close to a planet or dwarf planet, and tidal forces rip you apart into a ring. Move too far away, and the ring particles start sticking together, building clumps, and eventually turning into moons. This is the rule, the absolute golden rule of ring physics. Except Quaoar ignores it completely. Its ring is far outside the Roche limit, not a little bit, not barely, but dramatically outside, at a distance where, by all logic, the material should have already clumped into a moon. But it hasn't. It refuses to. This ring just sits there, wide, stable, intact, acting like the Roche limit doesn't matter. And that is why Quaoar is now one of the most fascinating objects in the Kuiper Belt. Because if one dwarf planet can break the rule, maybe the rule is incomplete. Astronomers spent months double-checking the measurements. They re-examined the star occultation data. They ran simulations. They asked the same question over and over. How is this ring stable? Why hasn't it turned into a moon? One idea is that the ring may contain too much gas or too many fine particles, preventing clumping. Another idea is that Quaoar's rotation or subtle gravitational quirks might be stirring the ring just enough to keep it from sticking together. Some even think there might be a small moon hidden within the debris, constantly disturbing the ring and preventing formation. But none of these explanations fully match what we're seeing. Quaoar is still beating the models. still challenging the idea of what a ring can be, still refusing to obey physics as we understood them. And here's where things get even more interesting. Quao-R doesn't just break the Roche myth, it bends the entire story we tell about ring formation. We usually explain ring formation in 3 simple ways. First, a moon can be torn apart by tidal forces. Second, debris from impacts can collect and form a thin halo of particles. And third, the Roche limit keeps loose material from clumping together into a new moon. But Quao-R forces us to add a 4th possibility, one no one expected. A ring can survive far outside the Roche limit in a place where it shouldn't exist at all, simply because we still don't understand every mechanism shaping it. When astronomers discovered Quao-R's ring in 2023, it immediately made them reevaluate assumptions about other distant worlds. If Quao-R can have a stable ring outside the Roche limit, could other dwarf planets have distant rings too? Could the Kuiper Belt be filled with ghostly, hard-to-detect rings around objects we barely know? Could some of the strange light curves we've seen in the outer solar system actually be caused by ringed bodies instead of odd shapes? Every new discovery out here opens another door. Quao-R is small, only about 1,100 kilometers across, not even half the size of Pluto. Not even big enough to be round if it weren't dominated by ice. And yet, this tiny frozen world has just rewritten one of the fundamental ideas about how ring systems behave. That is the beauty of the outer solar system. Out here, nothing fits the rules we expect. Out here, small objects can overturn big theories. Out here, even a quiet, icy dwarf planet can throw physics a curveball. And Quao-R is our reminder that rings are not simple. They are not predictable. They do not play by one set of rules. They are shaped by chaos, collisions, temperature, dust, rotation, and time, all interacting in ways we barely understand. Saturn may have the most photogenic rings, but Quao-R has the most rebellious ones. And this is only the beginning, because if a tiny world in the Kuiper Belt can break the rules, it means the rules themselves are not as solid as we thought. When astronomers confirmed Quao-R's ring and its impossible orbit, it did more than surprise them. It forced them to stop, rethink, recalculate, and in some cases, rewrite what they thought they knew about how rings form and how they survive. Because if a ring can survive in a place where physics says it shouldn't, then something fundamental about ring dynamics is missing from our models. And that changes everything. For decades, the Roche limit has been one of the most reliable tools in planetary science. It tells us where rings can exist and where they can't. It explains why Saturn's rings stay rings, why moons form outside that boundary, and why certain structures break apart under gravity. It has been a dependable rule, but Quao-R is breaking it, not bending it, breaking it. Its ring is too far out, too stable, too intact. There's no sign of clumping, no signs of moon formation, no signs of the particles trying to stick together like they should at that distance. And this is exactly why Quao-R matters, because if one object in the Kuiper Belt can violate the Roche limit so clearly, then other objects might be doing it too. We just haven't detected them yet. This means our understanding of how rings form, how they survive, and how they evolve may be incomplete. Scientists are now asking new questions. What if ring stability depends more on temperature than distance? What if ultra-cold environments slow clumping so much that rings can last far longer? What if collisions between particles are too gentle to trigger sticking? What if tiny shepherd moons, too small to see, are keeping the ring stirred up? What if the classic Roche limit formula doesn't fully apply to icy bodies? Every possibility forces a shift in thinking. And that's the real impact of Quao-R's ring. It isn't just strange. It challenges the foundation of ring physics. It tells us that even the simplest rules in planetary science can break down under the right conditions. This is how science moves forward, not from perfect theories, but from anomalies, the outliers, the exceptions, the discoveries that refuse to fit the model. Quaoar is one of those exceptions, and its importance goes even deeper. If rings can exist outside the Roche limit in the Kuiper belt, then some distant worlds may have rings we've completely missed. Rings so faint, so wide, or so cold that modern telescopes barely detect them. This could explain unusual dips in starlight, unexpected brightness changes, and odd occultation patterns in other observations across the outer solar system. Quaoar may be the first clue in a much bigger puzzle. And then there's the long-term consequence, our understanding of ring lifetimes. How long rings last before forming moons or collapsing may be completely off. If a ring outside the Roche limit can remain stable for long periods of time, then some rings we thought were short-lived could actually survive for millions of years. Others that we thought should already be moons might stay rings far longer. This affects models for Saturn, for Uranus, for Neptune, for Jupiter, for dwarf planets, even for objects in other solar systems. It pushes us to ask whether exoplanetary rings, especially around cold giants, could be more common and more stable than we thought. And all of that comes from one quiet dwarf planet that most people have never heard of. This is why Quaoar matters. A small icy world, 1,100 kilometers wide, has just forced scientists to rethink an entire category of orbital mechanics. It reminds us that the solar system is not finished teaching us lessons. It reminds us that out past Neptune, in the cold and the dark, some of the most important discoveries are still waiting. And the next strange, rule-breaking world might be even more surprising. As we move deeper into the outer solar system, everything becomes stranger. Smaller worlds, colder environments, older surfaces, and behavior we still struggle to explain. Quaoar is a perfect example of that unpredictability. Its rule-breaking ring shows us that the physics of these distant regions isn't as simple as we once believed. But before we go further outward, there's something important waiting back at Saturn. Something that helps us understand the opposite side of this story. If Quaoar shows us how rings can defy expectations, Saturn shows us how rings can be controlled, sculpted, and maintained with incredible precision. Inside Saturn's ring system, we find some of the most delicate gravitational engineering anywhere in the solar system. And the surprising part is this. The work isn't done by planets or massive forces. It's done by tiny moons. These are the shepherd moons, small worlds, some barely tens of kilometers across, that spend their entire lives guiding, nudging, and corralling trillions of ring particles into razor-thin structures. Without these moons, Saturn's rings would spread out, blur, and eventually dissolve into chaos. But thanks to these little gravitational sculptors, the rings stay sharp, defined, structured, and breathtaking. Two of the most famous shepherds are Prometheus and Pandora, tiny moons that guard the edges of Saturn's F-ring. The F-ring is one of the strangest rings in the entire solar system. It's thin, flexible, constantly shifting, and full of twisted strands that seem to braid and unbraid themselves over time. In some images, it looks like a single ring. In others, it splits into multiple strands. Sometimes it carries knots of material. Sometimes it sends out bright dust jets, but none of that behavior is random. Prometheus and Pandora are controlling it. Prometheus orbits just inside the F-ring. Pandora orbits just outside it. Together, they act like a pair of guards, one pushing inward, the other pulling outward, trapping the ring between them. Every time Prometheus swings close, its gravity tugs on the ring and pulls out long streamers of material. These channels and kinks are visible as bright streaks in Cassini images, stretching across the ring like scratches in frost. A few hours later, Pandora comes around on the other side and tugs the material back. This constant gravitational back and forth keeps the ring narrow and prevents it from drifting away. It's orbital choreography, precise, repetitive, and endlessly dynamic. And what makes it even more fascinating is how small these moons actually are. Prometheus is only about 100 kilometers across. Pandora is even smaller. Yet these tiny worlds are shaping a ring system hundreds of thousands of kilometers wide. This is one of the great lessons of Saturn's rings. Size does not determine influence. Gravity does. And gravity, even from a small object, can sculpt something enormous if it acts consistently over millions of years. Shepherd moons don't just guard the F-ring. They operate throughout Saturn's ring system. Pan and Daphnis, for example, live inside the Encke Gap and Keeler Gap. These moons are shaped like flying saucers, with equatorial ridges formed by collecting ring material over time. As Pan and Daphnis orbit inside these gaps, they create waves, literal waves, along the edges of the rings. These waves are not metaphorical. They ripple outward like ripples on water, except they're made of ice and dust. Every orbit, the moons pass by, tugging particles upward and downward, creating vertical waves that rise higher than Mount Everest relative to ring thickness. And this is where the beauty of Saturn's rings becomes undeniable. They are not static. They are constantly shifting under the influence of these shepherd moons. The rings are a living system, dynamic, ever-changing, and shaped by countless small gravitational interactions. We often imagine the solar system as quiet and still, but here at Saturn, the reality is much more like a dance. Moons orbit. Rings respond. Gravity reaches out across thousands of kilometers and leaves its mark. Prometheus tugs the ring outward. Pandora tugs it inward. Pan carves a gap. Daphnis waltzes through another. And the ring particles, countless billions of them, follow every cue. It's a choreography that has been running for millions of years, and yet it still feels fresh, chaotic, and slightly unpredictable. Without these shepherd moons, Saturn's rings would not look the way they do today. And in the distant future, when the rings begin to fade and collapse, these tiny moons may be the last witnesses to the greatest ring system the solar system ever produced. Shepherd moons remind us that even the smallest bodies can play enormous roles, and that sometimes the most delicate cosmic structures are held together by forces we barely notice at first glance. And speaking of delicate structures, the next mystery takes us to something even more surprising. The idea that rings aren't just passive debris fields. They are active systems. They evolve, they transform, and in certain conditions, they can cross the line from simple collections of particles into something much larger. Because as strange as it sounds, rings can give birth to moons, and moons in return can give birth to new rings. This is one of the most surprising cycles in the entire solar system, a cycle of creation and destruction that has been happening quietly for billions of years. Let's start with the basics. When material in a ring starts to clump together, when particles collide gently, stick, and build up mass, something begins to happen. Gravity takes over. Tiny grains become pebbles, pebbles become boulders, boulders become chunks, and eventually, those chunks grow large enough to pull in more material and form something new. A moon. This is exactly how scientists think many of Saturn's smaller moons formed, especially the ones near the edge of the main rings. They are ring children, born from the debris of a larger moon that once existed, torn apart by Saturn's gravity, and then rebuilt into new worlds. Moons like Pan and Atlas may be leftovers from this ancient process. Their strange flying saucer shapes are not coincidence. They are covered in ring material that has collected around their equators. These moons are literally sweeping up the outer edges of the rings as they orbit, growing wider and flatter over time. It's a process we're watching in slow motion, and the cycle works in reverse too. While rings can create moons, moons can also create rings, usually in the most violent way possible. A close moon can be shredded by tidal forces if it drifts inside the Roche limit. It only takes one moment of instability, a change in orbit, a passing body, or slow inward drift over millions of years. When that happens, the moon is pulled apart into fragments. Those fragments spread out, forming arcs, then bands, and eventually a full ring system. This is likely how Saturn's current rings formed. A past moon, possibly as large as a small world, drifted too close, got torn to pieces, and left behind the dazzling structure we see today. Mars is heading toward this fate as well. Its moon Phobos is slowly spiraling inward, losing altitude every year. In about 30 to 50 million years, it will cross its own Roche limit and break apart, forming a temporary ring around Mars. And for a while, Mars will have a ring system of its own, until the fragments eventually fall to the surface like a slow meteor shower. The cycle never stops. Rings become moons. Moons become rings. Creation leads to destruction, and destruction leads to creation. This cycle isn't limited to Saturn or Mars. In the outer solar system, around the dwarf planet Haumea, we find a ring that likely formed from impacts on its icy surface. In the asteroid belt, the small body Chariklo has two thin rings that may have formed from a collision or a shattered satellite. And even Pluto and Charon may have gone through ring phases early in their history before settling into the binary system we see today. The evidence is everywhere. Rings and moons are not separate categories. They are connected stages in the life cycle of worlds. What makes this story even more fascinating is how fragile the process is. If particles collide too hard, they break apart instead of sticking. If a moon forms too close to the planet, it gets pulled back in and destroyed. If a moon forms too far out, it escapes the influence of the ring and wanders off on its own. If shepherd moons disturb the ring too much, formation stops entirely. If the planet's gravity is too strong, the ring collapses faster than clumping can begin. Every ring system is a delicate balance between creation and destruction, one that can tip at any time. This is why Saturn's rings look different today than they did tens of millions of years ago. It's why Uranus and Neptune's rings are so thin and sparse. It's why Jupiter's rings are faint and continuously replenished by dust from its inner moons. Everything is in motion. Everything is evolving. Nothing stays the same. And this idea, this constant cycle, forces us to think of rings not as static structures, but as temporary phases in the lives of planets and moons. Some rings are newborn, some are ancient, some are dying, some are already transitioning into prototypes for future moons. Right now, around Saturn, we can actually see bright clumps forming in certain ring segments, material that may one day become a new generation of tiny moons. Most won't survive. A few might. A handful could grow into something bigger over millions of years. It's a system in motion, a system building and destroying worlds at the same time. And the more we study these rings, the more we realize we're witnessing a process that shaped the entire solar system, including Earth. Because Earth's own moon was once part of a debris disk, a ring around a young, battered planet, a ring that collapsed, clumped, and became the world that lights our night sky. Every ring carries the potential to become something more. Every moon carries the possibility of returning to dust. It's a cycle as old as the solar system itself, and it's still happening today. And with that in mind, we can now move toward one of the most fascinating consequences of this cycle. What happens when gravity, resonance, and sheer chaos collide? To answer that, we don't have to look at Saturn, or Quaoar, or any distant world. We only have to look at Earth, because in 2024, researchers uncovered something extraordinary, something that completely reshapes our understanding of our own planet's past. Earth once had rings, not theoretical, not imagined, not a fringe idea. Real rings, circling above ancient oceans 466 million years ago. And here's the part that shocked scientists. We didn't discover this with telescopes. We discovered it through craters. Let's break it down. During the Middle Ordovician period, Earth suddenly experienced a massive spike in meteor impacts. Dozens of craters around the world, in Sweden, China, Russia, and the United States, all date back to roughly the same moment. For years, geologists thought this event came from a single asteroid family breaking apart, but the numbers didn't add up. There were too many impacts, spread too evenly, for that explanation to make sense. Then a new idea emerged, one supported by orbital simulations and crater timing. Earth wasn't just hit by stray rocks. Earth was hit by the remains of its own ring system. Here's the scenario scientists now think happened. A large moonlet, a smaller companion to our modern moon, drifted too close to Earth. Gravity tore it apart. The debris spread out into a temporary ring. And over the next few million years, those ring fragments slowly decayed and fell onto the planet's surface. A rain of rocks that lasted long enough to leave a geological fingerprint across multiple continents. This is one of the clearest examples of the cycle we just explored: rings forming moons, and moons becoming rings again. Except this time, the story involves us. If Earth had rings, even briefly, the sky would have looked completely different. A bright arc stretching across the horizon, a glowing band over ancient oceans, the kind of view we normally associate with Saturn, happening right here on our own world. And the evidence lines up. Multiple craters dated to the exact same geological window. High concentrations of L-chondrite material. Sudden cooling events tied to dust entering Earth's atmosphere. Orbital simulations showing stable temporary rings forming after a breakup event. All of it points to the same conclusion. Earth did, in fact, have rings. Not for billions of years, not long enough to leave permanent marks in the sky we know today, but long enough to reshape climate, geology, and the planet's impact history. This discovery matters because it proves something important. Rings are not exotic. They are not limited to Saturn or the gas giants. Under the right circumstances, any planet, even Earth, can have rings. And that changes the entire way we think about ring systems. Rings are not decorations. Rings are not rare. Rings are phases, temporary chapters in a planet's life cycle. Earth had one of those chapters, a brief chaotic moment where our planet looked more like Saturn than the world we know now. And once you accept that, another question becomes unavoidable. If Earth could have rings, how many other planets once had them too? How many ring systems have come and gone across the solar system? How many stories of creation and destruction have already vanished? This new discovery isn't just a footnote. It's a reminder that ring systems are dynamic, appearing, evolving, collapsing, and sometimes falling onto the planets that created them. We've seen what ancient rings did to Earth. Now it's time to look at a world where the next ring system hasn't happened yet, but the countdown has already started. Because above Mars, right now, a death spiral is unfolding in slow motion. Phobos, the innermost moon of Mars, is dying. Not figuratively, not symbolically, literally. Every single year, Phobos drops a little lower in its orbit, only a few centimeters, but always downward, always closer to Mars, always losing altitude. And once you start falling toward a planet, there's no turning back. In 30 to 50 million years, Phobos will cross a point called the Roche limit, the same gravitational boundary responsible for tearing moons apart around Saturn, Uranus, Neptune, and possibly Earth in the past. When Phobos reaches that line, one of two things will happen. Either it will crash into Mars, or it will be ripped apart and form a ring. And current models show the second option is far more likely. Imagine a future Mars with a thin, ghostly ring arching across its red sky. A ring created from the shattered remains of its closest moon. A ring that wouldn't last forever, but would circle the planet long enough to reshape its atmosphere, its dust cycles, and eventually its surface. It sounds dramatic, but we're already seeing the first hints of what's coming. Phobos is covered in long parallel grooves carved into its surface. For years, scientists thought they were impact scars, but new simulations show there's something else entirely. Stress fractures, cracks forming because Mars is already pulling Phobos apart. The moon is being stretched, distorted, and slowly weakened as it spirals inward. The fractures are early warning signs of a breakup event that hasn't happened yet, but absolutely will. And when the end arrives, it will be violent. Phobos will be shredded into chunks, ranging from dust to boulders. Those fragments will spread out along its orbit. Mars will catch them, redistribute them, and reshape them into a ring that could last millions of years. A ring that future explorers, or future civilizations, might witness from the Martian surface. And the strangest part? This process isn't rare. It's not unusual. It's not even surprising. This is the same cycle we've been following across the solar system. Moons become rings. Rings become moons. Creation, destruction, recreation. It happened around Saturn. It happened around Chariklo. It happened around Quaoar. It happened around Earth. And it will happen again around Mars. A moon dying, so a ring can be born. If Phobos shows us the beginning of Mars' transformation, then its future ring system shows us the end of the cycle and what comes after. Because Mars doesn't just have a doomed moon. Mars has a history, a ring history, a cycle it has already lived through before. Scientists now believe Mars may have had rings multiple times in the past, rings that formed, collapsed, and reformed as its two small moons evolved. And Phobos, it's simply the next chapter. To understand the future, we start with the basics. When Phobos finally crosses the Roche limit, gravity will tear it apart. Chunks of rock and dust will spread along its orbit, gradually stretching into a thin band. That band will grow wider, fainter, and more stable over time until Mars becomes a ringed planet. A world with a halo of debris circling above its dusty red deserts. But this ring won't look like Saturn's broad, icy masterpiece. Mars' ring will be smaller, darker, made mostly of rock dust instead of clean ice crystals. Under sunlight, it may resemble a faint charcoal ribbon encircling the sky, visible at certain angles, nearly invisible at others. From the ground, future settlers might see it as a thin arc stretching across the night, a ghostly reminder of the moon that once existed. And here's the twist. This won't be permanent. As the ring ages, the smallest particles will slowly drift toward Mars. They'll burn up in the atmosphere as streaks of light, a slow, silent meteor shower lasting hundreds of thousands of years. Larger fragments will follow a different path. They'll spiral outward and start clumping again. Under the right conditions, they could form a new moon, a replacement for the Phobos that was lost, a moon born from a ring born from a moon. The same cycle we've watched at Saturn, Quaoar, Chariklo, and long ago, even Earth. And the reason this cycle is so strong at Mars is because its moons are fragile, small, low density, easily disrupted. Phobos is the first to go, but not the only one at risk. Deimos, the outer moon, although more stable, may also have a ring history. Some researchers believe Deimos was once part of a larger moon that broke apart, sending debris inward to form earlier Martian rings. Evidence of this includes Deimos's unusually tilted orbit, the size difference between the moons, models showing repeated moon breakups over billions of years. Put together, it paints a picture of a planet that has worn rings more than once. Rings that formed, faded, returned, disappeared, and are now preparing to appear again. Mars may not be a gas giant, but it is a world shaped by the same forces that sculpt the outer solar system: gravity, resonance, orbital decay, and the relentless pull that turns moons into dust. and Phobos's destruction will be the most recent expression of that cosmic pattern. In the end, Mars' future ring won't just decorate the sky. It will rewrite the planet's atmosphere, alter dust cycles, change meteor patterns, and slowly reshape the surface. It will be Mars wearing the memory of its moon, a world marked by its own history and by a cycle as old as the solar system itself. Rings don't have a single origin story. They aren't created one way and they don't evolve one way. Instead, they're the product of a chaotic universe where destruction, chance, timing, and gravity all compete at once. And that's why ring systems are so unpredictable. Some rings come from collisions, others come from tidal disruption. A few are leftovers from the earliest days of the solar system. Each ring carries a different past, and every origin tells us something about the world that hosts it. Let's break down the main possibilities. First, the collision scenario. This is one of the most violent paths. A moon gets hit by something big, an asteroid, a comet, or even another moonlet, and the impact scatters debris into orbit. If enough of that material stays above the planet's atmosphere, it forms a ring. This is the scenario scientists believe happened around Chariklo, Haumea, and possibly around Earth in the Ordovician period. In these systems, rings weren't gentle byproducts. They were scars, the aftermath of cosmic accidents. Second, tidal disruption. This is the slow, quiet killer. A moon drifts inward over millions of years, getting closer to the planet it orbits. Eventually, it crosses the Roche limit, and gravity rips it apart. No explosion, no collision, just a moon pulled to pieces, strand by strand. This is the fate waiting for Phobos. It's likely the fate that created Saturn's rings. And simulations show it may have happened around other planets we haven't studied in detail yet. Tidal disruption is elegant in a way, a kind of gravitational recycling that makes rings out of moons and moons out of rings. Third, leftover planetary formation material. This is the oldest path. Before the solar system settled into the structure we know, planets formed inside swirling disks of dust and gas. Most of that material clumped into planets and moons, but not all of it. Some fragments were left behind. In places like Jupiter and Neptune, faint, dark rings may be remnants of that ancient era, the leftovers of worlds that never fully formed. Tiny particles kept in place by weak gravity and delicate balance. These kinds of rings are subtle, thin, dusty, hard to detect, but they carry the signature of the solar system's earliest days, the original debris that helped build everything else. Fourth, cryovolcanic or surface-generated rings. This is the rarest scenario. Some rings are fed continuously by particles escaping from active moons. Jupiter's main ring is supplied by dust from the moon Metis. Mars' faint dust halo comes from impacts on Phobos and Deimos. Saturn's E-ring is created by the geysers of Enceladus, one moon maintaining an entire ring on its own. These rings don't come from destruction. They come from activity, a steady outflow of particles that replenish the ring over time. One moon acts like a generator. The ring becomes its atmosphere in orbit. And finally, hybrid origins. The truth is that many rings didn't come from just one event. Some begin as impact debris, then evolve under tidal forces. Others start as ancient dust and get mixed with new material from active moons. Some begin thin and turn thick. Others begin bright and fade into darkness. No two ring systems share the same path. Each one is shaped by the planet's gravity, the moon's stability, the distance from the sun, the temperature of the system, and the long list of events that happened over billions of years. This is why rings continue to surprise scientists. Why Quaoar breaks the rules. Why Saturn's shepherd moons sculpt structures thinner than paper. Why Mars may have worn rings more than once. Why Earth had rings long before humans existed. Rings are not decorations. They're evidence. Evidence of violence, timing, decay, creation, and history. They show us the scars of the solar system, and they show us the moments where worlds were changed forever. Now that we understand how rings form, we can move to a deeper question, one that takes us beyond origins and into the behavior of rings themselves. Because once a ring exists, it doesn't just sit there. It moves. It spreads. It warps. It falls apart. It evolves. If rings in our own solar system are unstable, shifting, and shaped by chaos, then imagine what rings might look like around planets far beyond the sun, places with stronger gravity, larger moon systems, and completely different environments. Because the biggest ring system we've ever found isn't around Saturn or Jupiter or any world we've ever sent a spacecraft to. It's around a planet 200 light years away, a world called J1407b. This exoplanet doesn't just have rings. It has a ring system 200 times larger than Saturn's. So wide that if it replaced Saturn's rings in our sky, they would stretch across the distance between Earth and the Moon. That's not poetic exaggeration. That's the scale. The rings surrounding J1407b are so massive that when the planet passed in front of its star, the rings blocked out more light than the planet itself. Astronomers weren't looking for rings when they found it. They were simply analyzing a strange extended dimming pattern during a transit. But the shape of the light curve didn't match a planet. It matched a colossal disk of debris. The planet itself is young, only a few million years old, and the rings may be the early stages of moon formation. Dozens of future moons could be forming inside that disk right now. In other words, we may be watching an entire moon system being built in real time around another star. And this discovery changed everything. Because until J1407b, most astronomers assumed giant ring systems would be rare, temporary, hard to detect, too faint or too small to reveal themselves across light years. But now we know better. If one planet can have rings this large, there could be hundreds of similar systems out there, invisible by current telescopes, waiting for us to find them. And we are getting better at finding them. With missions like the James Webb Space Telescope, we can detect subtle dips in starlight that reveal not just planets, but the enormous halos surrounding them. We can detect warped light curves, partial transits, and the telltale soft edges that come from debris disks instead of solid planets. We are learning to read the signature of rings across the galaxy. Soon we may find rings brighter than Saturn's, rings darker than Mars' future ring, rings made entirely of rock, rings made of icy particles near newborn stars, rings forming moons before our eyes, rings decaying into planetary atmospheres, rings interacting with exomoons that haven't even formed yet. And here's the part that makes this search so important. Rings can tell us more about exoplanets than the planets themselves. A ring system reveals the planet's age, its temperature, its moon system, its gravitational strength, its collision history, even the material that built the planet in the first place. Rings are a window into the story of the world they orbit. And the more of them we find, the clearer our picture becomes of how common, or how rare, worlds like ours truly are. J1407b is just the beginning. A preview of a universe filled with ring systems, far stranger, far larger, and far more complex than anything we've seen in our own backyard. And as we keep searching, we'll learn something crucial about the cosmos. Rings aren't a local phenomenon. They're universal. They're everywhere. They appear, disappear, grow, collapse, and rebuild across billions of years, in our solar system and beyond it. Which leads us to an even deeper question. If rings are this common and this dynamic, what does that mean for the moons forming inside them? Because wherever there are rings, moons are never far behind. If moons are never far behind rings, then the next truth is even more surprising. Rings don't just shape moons. Rings shape planets themselves. And the greatest proof of this came from one of the most dramatic spacecraft endings in history, Cassini's grand finale. When NASA sent Cassini plunging into Saturn's atmosphere in 2017, its final orbital dives did more than deliver spectacular images. They revealed something no one expected. Saturn is eating its rings. Not metaphorically, not poetically, literally. Cassini's instruments detected streams of material, ice grains, dust, organics, and charged particles, falling off the rings and spiraling into Saturn's upper atmosphere like rain. This ring rain isn't slow or symbolic. It's intense. Saturn is pulling in thousands of kilograms of ring material every second, enough to erase the rings completely in the distant future. For the first time, we saw that rings aren't just ornaments orbiting a planet. They are active, interactive systems, constantly feeding, draining, exchanging, and reshaping the body at their center. This discovery rewrote the relationship between planets and their rings, because it means rings can change a planet's atmosphere, alter its chemistry, affect its magnetic field, modify its temperature, and even influence its long-term evolution. The rings are not passengers, they're participants. And this isn't unique to Saturn. The same exchange of material happens around Jupiter, Uranus, Neptune, and even faint ring systems around small bodies like Chariklo. Dust drifts inward, charged particles migrate, ionized gases interact with magnetic fields, and over millions of years, this slow rain of material becomes a subtle planetary sculptor. But Saturn gave us the clearest view. Cassini measured molecules like water vapor and carbon compounds falling from the rings into Saturn's atmosphere. This ring rain actually changes the composition of the atmosphere, creating dark streaks, chemical patches, and ionization regions that scientists never understood until Cassini dove between the rings and the planet. It showed us that Saturn's atmosphere isn't shaped by the planet alone. It's shaped by the rings above it. And there's something else. Cassini discovered that the rings aren't just falling into Saturn, they are also giving back. Material from Saturn's atmosphere flows outward too, interacting with the rings, charging particles, modifying orbits, and influencing the structure of the ring system itself. It's a two-way exchange, a feedback loop. Planet shapes ring, ring shapes planet, back and forth across millions of years. This relationship affects the thickness of the rings, the brightness of their bands, the behavior of shepherd moons, the rate at which moons migrate, the speed at which rings decay, and even the long-term stability of Saturn's entire system. Rings don't just decorate a world, they rewrite it. They change the chemistry. They change the orbits of moons. They change the flow of energy. They change the evolution of the system. And this insight brings us to a bigger realization. Rings are not passive leftovers. They are engines of change. Wherever we find rings, in our solar system or around distant exoplanets, those rings are actively reshaping the worlds beneath them. Moons, planets, rings. They're all connected in a cycle that spans billions of years. And now that we understand how rings shape planets, we can take the next step. What happens when you run this cycle long enough? When moons fall, rings form, rings fall, moons form again. Over and over for billions of years, you get worlds that age in ways we never expected. Worlds that transform. Worlds that evolve. Worlds that carry scars of ancient rings long after the rings vanish. And that brings us to one of the most dramatic consequences of all, the destinies of rings themselves, where they go, how they end, and what traces they leave behind. If rings can shape planets, steer moons, and rewrite entire systems, then we have to face the undeniable truth they all share. Rings don't last. They are temporary. They are fragile. They are moments, cosmic moments, in the long lifetime of a planet. Some rings are young, some are ancient, some are already fading, and some haven't even formed yet. To understand why, we need to look at what rings really are: collections of particles on borrowed time. Every piece of ice, dust, and rock in a ring is constantly being pushed, pulled, charged, eroded, vaporized, reassembled, and broken apart again. Rings look serene from a distance, but up close, they're violent ecosystems of collision and motion. And that's why rings don't survive forever. Let's break down the reasons. First, rings spread out over time. Particles bump into each other. Even tiny collisions transfer energy. That makes the ring widen, slowly at first, then faster. Eventually, the particles drift so far apart that the ring becomes too faint to see, or it collapses inward onto the planet. Second, planets absorb rings. We saw this with Cassini's grand finale. Saturn is pulling its rings into its atmosphere like rain. This process happens to every ring system in some form. Gravity wins. The planet consumes its halo. Third, radiation destroys ring particles. Sunlight erodes icy grains. Charged particles from planetary magnetic fields bombard dust. Over millions of years, the fine material evaporates, leaving only heavier debris, and most rings don't have enough of that to survive. Fourth, moons disrupt rings. Moons can stabilize rings, but they can also break them apart. A passing moonlet can stir the particles, scatter them, or sweep them up entirely. Fifth, the solar system is messy. Comets crash through rings. Asteroids strike moons. Resonances shift. Orbits change. A single collision can erase millions of years of ring history in an instant. Put all of this together, and you get a bigger picture. Rings are temporary phases, not permanent features. Saturn's rings, the most majestic in the solar system, may be only 100 million years old, young, recent, practically newborns compared to the age of the planet itself. In cosmic time, they might vanish in the blink of an eye. Uranus's rings may be older, narrow, dark, survivors of a violent past, but even they will fade eventually. Jupiter's rings are already faint and dusty, more like a memory than a structure, constantly replenished by impacts on its inner moons. Neptune's rings are incomplete, arcs, fragments of something larger that didn't survive. Chariklo and Haumea have rings so delicate they may last only a few million years before scattering into space. And Mars' future ring, born from the destruction of Phobos, will be temporary too. A brief halo around a red world before the particles fall as a slow rain back onto the surface. Even around distant exoplanets like J1407b, colossal rings sculpting moon systems won't last forever. Eventually, they'll collapse, clump, or drift away. This is the cosmic dance we've been watching. Creation, destruction, rebirth. A moon forms. It moves inward. It breaks apart. A ring appears. The ring spreads. Pieces clump again. A new moon is born. Over and over, across billions of years, this cycle shapes entire worlds. And the wild part is this. When we look at a planet with rings, we're catching it in a rare stage. A moment when the violence and beauty of planetary evolution are on full display. Rings are warnings. Rings are relics. Rings are predictions. They tell us where a system has been and where it's going next. And now that we understand how rings live and die, we can finally look ahead toward the distant future of these systems and what happens when entire ring cycles come to an end. For everything we've uncovered about rings, their origins, their lifespans, their transformations, there is still a list of questions so large that it keeps planetary scientists awake at night. Because the truth is simple, we still don't understand everything, not even close. Every new discovery opens two more doors. Every solved puzzle reveals another layer. And the more we learn, the stranger these ring systems become. Let's start with one of the biggest mysteries. Why do some rings defy physics? Quaoar's distant ring should not exist. It should have collapsed into a moon. It should be unstable. It should violate every rule we teach about the Roche limit. And yet, it's there, perfectly intact, completely silent, daring us to explain it. We don't have the answer. Then there's Neptune's rings. Why do they form arcs instead of full circles? Why do the arcs resist spreading? Why do they behave like clusters held in place by forces we barely understand? No simulation fully matches what we see. Another question: how many rings have existed in the past? Earth had rings. Mars will have rings. The gas giants may have had massive rings billions of years ago, rings that left no trace except in the orbits of their moons. Did Venus have rings after ancient collisions? Did Mercury wear a ring when the early sun was more violent? Did Jupiter once have a bright ring that collapsed long before anyone could witness it? We don't know. And then there are the mysteries around the smallest ring worlds. Why do tiny bodies like Chariklo and Haumea have rings at all? How can an object barely a few hundred kilometers wide maintain a stable ring system that even survives rotation, collisions, and solar radiation? Are there dozens more ringed asteroids we haven't discovered yet? Speaking of undiscovered rings, how many exoplanets have rings so massive they dwarf our entire solar system's structures? J1407e was a surprise, a ring system 200 times larger than Saturn's. If one planet can do that, how many more are waiting? How many young systems are growing moons inside enormous disks we haven't detected yet? How many ancient systems are losing their rings right now? We still don't know. And then there's the question scientists rarely ask out loud. Why do some planets have rings while others don't? We know the mechanics, the rules, the orbital physics, but there's an underlying pattern we haven't cracked. Why Saturn and not Jupiter? Why Quaoar and not Eris? Why Chariklo and not most asteroids? We're missing something, some deeper governing principle that decides when rings appear, when they vanish, and which worlds are chosen. And that's exactly why future missions matter so much. Europa Clipper will help us understand icy material and orbital interactions on a level we've never reached. Dragonfly, heading for Titan, will reveal how surface chemistry and atmospheric processes might interact with early ring remnants. Possible missions to Enceladus and Uranus could show us how moons and rings exchange particles across magnetic fields. And the next generation of telescopes, the extremely large telescope, the Habitable Worlds Observatory, and future infrared surveyors, will let us detect faint, cold ring systems around distant exoplanets with unprecedented clarity. Each mission is a key. Each observation is a puzzle piece. Each discovery gets us one step closer to understanding how rings shape the evolution of worlds. But here's the truth. For now, we live in the era of questions, the era of mysteries, a time when we know just enough to be amazed, but not enough to be satisfied. Rings are more than decorations. They are clues. They are warnings. They are ancient records of events we never witnessed, and predictions of events still to come. And until the next wave of missions finally answers these questions, we're left staring at the sky, knowing that the solar system and the universe is still hiding some of its greatest stories inside those thin, fragile bands of dust and ice. After exploring every mystery, every cycle, every collapse and creation of rings across our solar system, a final truth becomes impossible to ignore. Rings aren't rare. They're fundamental. They are not the exception. They are the rule. The moment you step back and look at the full picture, you begin to see the pattern. Earth had rings. Mars will have rings. Saturn wears them now. Uranus and Neptune guard their thin, dark bands. Jupiter hides a faint halo that only appears under perfect light. Tiny asteroids like Chariklo carry rings of their own. Dwarf planets like Quaoar break the rules entirely. And far beyond our sun, planets orbiting distant stars have ring systems so massive they make Saturn look small. When you zoom out far enough, a realization settles in. We are living in a universe decorated with cosmic jewelry. Every ring tells a story. A moon destroyed, a moon being born, a collision long forgotten, a gentle rain of particles shaping a planet's atmosphere. A cycle that repeats across billions of years and billions of worlds. Rings are time capsules. Rings are warnings. Rings are blueprints of how solar systems form, evolve, and eventually fade. They show us where a world came from and where it is going. When we look at Saturn's bright bands, or Quaoar's impossible ring, or the ghost ring forming above Mars, we're not just observing distant objects. We're watching the universe build itself. We're witnessing creation and destruction happening on a scale so vast that it reshapes planets, moons, and everything around them. And that's the heart of this journey. Rings aren't background scenery. They're active forces shaping the past, present, and future of every world they touch. And as new telescopes, new missions, and new discoveries arrive, we're going to learn even more about these fragile structures and the stories they hold. Because the universe is still full of rings we haven't found yet, still full of moons waiting to be born, still full of worlds wearing halos in the dark. And here, at the end of this exploration, we want to thank you for being part of this journey, this deep dive into the hidden architecture of our solar system and beyond. If you've enjoyed this exploration, consider supporting Whispering Wonders of Science by liking the video and subscribing to the channel. It helps more than you know, and it ensures you won't miss the next adventure waiting just beyond the horizon. We'll be back soon with more wonders to uncover, more mysteries to illuminate, and more stories whispered by the universe itself. Until then, keep looking up and keep listening to the quiet, extraordinary secrets of the cosmos.